Hello Science Alliance, I am Lara, this is State of Science. I've been streaming free live lessons into internet for nearly 6 years, and you have come into the very middle, basically, of my IGCSE physics course. So, no, not the middle, no. We're sort of skidding towards the end actually, aren't we? But anyway, we're right in the middle of the topic of magnetism. Now is not a good time to start watching. You're very welcome to stay, just don't, if you find it all really hard, don't get freaked out and think that physics is awful. It can be awful, but this is just that other people have learned stuff in other lessons that you haven't learned, so that's why it might be confusing. Right, that said, I will right now pretty much recap everything we've done in the magnetism lesson so far, because it's all been coming down to this, chums. It's all been coming down to talking about transformers and how electricity is made. So if I show you this picture, can you tell me what this is? Lara, it's a piece of wire attached to a cell. Yeah, but what actually is it? What happens when you run a current through a bit of wire? So you've got a battery here. We'll talk a lot about potential difference today, or voltage. One end of the battery is a little bit positive, one end is a little bit negative. So it means that, anyway, I'm getting ahead of myself. Electricity is flowing through this bit of wire. What happens when charged particles move? We get an invisible force field around the wire, don't we? So this is in fact an electromagnet. Charged particles generate magnetic fields. Just what an amazing, amazing planet we live on. Charged particles generate magnetic fields. So moving charged particles, I should say. So because there's electrons in this wire that are moving, we've got an electric field around it, and we call it an electromagnet. You want to make the electromagnet stronger? You can add an iron core. Because that iron core gets magnetised when it's in the magnetic field, and then we get an even stronger magnetic field around it. Hooray. You use iron, remember? Because iron's a soft magnetic material, so when it's in the magnetic field it becomes magnetic, but then if you unplug the magnet you can turn the iron sort of immediately becomes not magnetic anymore. So you get the magnetic field of the wire and the magnetic field of the iron core. Lovely. All right. Do you remember this? I said we had to research, we had to go back over everything very quickly. You remember this? It's called the left hand rule, the left hand grip rule. You get your left hand, you make a little thumbs up, you make it that it's a very loose thumbs up so that your fingers are sort of curling around. If your thumb's in the pointing in the direction that the current is flowing, then your loosely curled fingers will show the direction that the magnetic field is going in. I mean, again, if you're new, I really hope you're not. Magnetic fields always go from north to the south. So in this situation, if the current is flowing up the screen through this wire, then our right hand thumb grip rule is showing us that if the current is moving in the direction of my thumb, then the magnetic field is moving anti-clockwise like that. But you can do it the other way around. If the current is moving in a circle, you could put your fingers in the shape that the current was flowing in, and the thumb would show you the direction that the magnetic field was going in. Let's have a look. It doesn't matter if we get it wrong, does it? What do you reckon? This is a deeply confusing diagram because I had to make it myself. Can you tell? So do you remember the convention is? It's not usually what is actually happening, but what we say is that current is flowing from positive to negative. So current is flowing through this wire from positive, so it's going like that, right? It's going into the screen and then out of the screen, into the screen and out of the screen. That's the direction that the current is going in. So how are those magnetic field lines moving? Is that right? Have I done that right? Going in and out and in and out. So I think it's going like that. I think my fingers are curving downwards. So my magnetic field is going to be in the direction of this thumb. So it's going to be the north, it goes from north to the south, remember? So I think that's going to be the north pole of my magnet, and that's going to be the south pole. So the left is the north. The question is, chums, have I got it right on the answer reveal? Hey, look at that. Wow, amazing. It's almost like I wrote the question. Wait, is that right? Oh, blooming heck, it's not, is it? Jeepers creepers, isn't it? Because no, it's not. From north to south. Oh, I've done it wrong. Oh, it's quick. Let's move on. Oh, it's embarrassing. There, look. I spotted it and I fixed it. That's better. From the north to the south. So that's the north pole of the magnet, because I can tell because the field lines are going to the south. So that would be correct. Well done, past me. One of the many past me's. So yeah, the reason we use iron in the middle of the electromagnet is because if you break the circuit, then immediately the iron becomes demagnetized and you get no more magnetic field. Okay, we need to do a little bit of electricity recap here, because we've sort of been talking about charged particles moving, and I've said a little bit about voltage, but some of you will have been to the electricity lessons and will sort of know this, and this will just be you trying to remember. Some of you won't know this at all. If not, don't worry about it. I'm going to try and give you everything that you need. Electrons in a wire. This is sorry, I'm so sorry. This is a terrible, terrible diagram. Just awful. Ugh. I've got to stop, because if there's any physics teachers watching, they will just be tutting so hard. Metal is very good at conducting electricity, okay? Because it contains free electrons. So atoms are positively charged particles, teeny tiny little negatively charged particles whizzing around the outside, okay? That's what an atom is. Wires, metals, are really good conductors of electricity because some of the electrons are free. Some of the electrons have broken off from their proton overlords and are free, but not all of them. On this diagram, I've made it look like all the atoms in metals just get ripped apart and electrons are whizzing past protons. That is not true. The atoms in metals are still atoms, protons with electrons moving around them, but there are some what we call free electrons. That is the answer that you would give in IGCSE. Why is metal good at conducting electricity? Or indeed heat, because it contains free electrons. But it's just a few of them. So anyway, you've got these little negatively charged electrons in a wire, and they can move. That's what electricity is, basically. Little electrons flowing. So we call this the current. The current is the rate of flow of the charge. Let's say that the electrons is the charge. It's how fast they're going. There you go. So if you, how much charge passes a certain point per second? If you were tiny and you were sat here with a little stopwatch, the amount of charge passing that point per second, that would be how much current is flowing, right? Voltage is like how much energy the charge has, energy per charge. But you'll also hear the word potential difference, and it's just worth me having a little chat with you about this now. I'm sorry, I know, it's a lot, isn't it? It's a lot of information. So in our forces lessons, we looked at how if you lift something up, you give it gravitational potential energy. If I lift up this pen, it's got the potential to fall, because like gravity can make it fall. There's a sort of difference between the ground and the pen, so it falls. Potential difference in electricity is kind of similar. If you've got a piece of wire and one end is a little bit positive and one end is a little bit negative, then the charges have the potential to move. So potential difference or voltage is basically like how much the charges are being pushed. In the same way that you can lift a pen really, really high, or you can have it just above the ground, and that changes how much energy it has. If you've got a really big potential difference, then the electrons will be pushed a lot. And if you've got a very small potential difference, you know, like a 1 volt battery or something, then they don't have as much of a push. All right, because we've got more. Here we go. So, current can be direct, like it can just flow in one direction, and that's all we've talked about so far. So that's direct current. And if you were going to draw a graph of what direct current looked like how the voltage changed over time, it would just look like this. So this is what batteries do. You've got like a 2.5 volt battery, you connect it to a wire and a light bulb, say, the voltage across that wire, it just stays the same. It does what it says on the tin. It's a 3 volt battery, then you've got a 3 volt potential difference across the wire, and as time goes by, it sort of more or less stays the same, yeah. You can get something called alternating current, which is where the current constantly changes direction. Oh, look, children, are you visualising that now because of my PowerPoint? And the voltage constantly switches. So this isn't what batteries do. This is in fact actually what the electricity that comes out of your plug socket does in your home. We will talk a lot more about this next lesson and also after half term. So with an alternating current, the charges go to and fro and to and fro and to and fro. The voltage, it goes from like peak to bottom to peak to negative. So if it was like a 3-volt alternating voltage, it starts at 3 and then it gets lower and lower and lower till eventually for like a split second you've got 0 voltage, and then lower and lower until it's what we call minus 3 volts, and then up again and down again and up again. And that's alternating current. Yeah, I'm just gonna, yeah, I'll move on. No, yeah. So what this means for our magnetic fields, because we've just looked at how, like, if you left hand and right hand, God, I'm so bad at this. We've looked at the right hand grip rule and how if the current is flowing just upwards, say, in the direction of your thumb, then the magnetic field would be coiling round in that direction. The current is constantly changing direction. So 1 second it's like that, and the next second it's like that, and then it's like that, and then it's like that. What do you notice about the magnetic field around that wire? Going that way, going that. So the magnetic field is constantly changing as well. Is that okay? So when there's just current flowing through a wire, you get a magnetic field around the wire. But when there's an alternating current in the wire going to and fro and to and fro and to and fro, the magnetic field also goes to and fro and to and fro and to and fro. Okay, so it's all starting to come together, chums. We've talked about electromagnets and how great they are for moving stuff like scrap metal around, because you can turn them on and off, you can pick them up, you've got a magnet, you can get a load of heavy metal, move it around, and then turn a switch, and the electricity stops flowing, so the magnetic field is no longer there, so the iron gets demagnetized, so the metal falls. Would you run alternating current or direct current through the wires, and why? Let's pretend that this is our electromagnet here, okay? So we've got current flowing through a coil of wire with an iron core. That's what an electromagnet is. If you want, you could do it with the right-hand grip rule. You can see that the current is flowing sort of into the screen on the right and then coming back out at you on the left and going into the screen on the right and coiling around and coming back out at you on the left, okay? So I'm going to say it's doing this awkward move here. Would you want that electromagnet to have alternating current running through it, current that is constantly changing direction, or would you want it to be direct current? Have I given you enough unsettling silent teacher seconds? Should we move on? You'd want it to be direct current, because if it was alternating, the magnetic field would be constantly changing direction, and there'd be a moment while the magnetic field was flipping that it had no magnetic field and the stuff would fall off. So the magnetic field, if this is the current flowing through the wire, the magnetic field will be doing that. So there'll be a split second where there's no magnetic field and yeah, you haven't got an electromagnet anymore. Okay, let's move on. Need to talk about power. Tiny bit. Again, some of you will half remember this from electricity, hopefully. But all you need to know if you're new is power is the amount of energy per second, basically. The amount of energy per second, and it's measured in watts. So we've been talking about how current is how much charge flows per second. And voltage, or potential difference, is like how much the charges are being pushed, like how much energy they've got. So all this means that there's another equation for power. You can say that power is current times voltage. I can feel how I would be feeling at this point in the lesson, thinking, what on earth? I don't understand. I don't get this. This is too awful. Don't worry, this is as awful as it gets. I am going to backtrack. I'm just having to hit you with loads of stuff because You have to have remembered it, or even have to have vaguely mentioned it before we do these questions. Right, so power, the amount of energy per second, if you like, being shifted, used by these charges, is current times voltage. Let's move on. That's just a little, don't worry if you don't get all this, don't panic, chums, it'll be fine message on the board there. Okay, we've looked at things like this already. Do you remember this? We looked at this last week. Say you get a coil of wire, just a regular old coil of wire, which is attached at both ends, so it's a constant loop, and you move a magnet in it. Is there a potential difference across that wire, and is there a current flowing? Can you remember? This is just revision from last week, but it's all got very complicated, hasn't it? There's so many different hands rules. So if charges are moving, if you've got wire that has got a battery in it, so you make a current flow, you get a magnetic field. But if you've just got a wire, just a regular old bit of wire with no battery attached, and you make magnetic field lines cut through that wire. Do you remember last week? I had the magnets on the board and I was going like that, and we were cutting Play-Doh, and I was saying you can just get a scrap of wire and move it between two magnets and you will get a potential difference across the wire. But if it's a complete circuit, then you'll get even a current flowing, even though there's no battery attached, just a bit of wire. If magnetic field lines are cutting through it, you will make the charges flow. Amazing. So in this situation, we said, yeah, there is a potential difference across the wire because you've got a magnetic field here, which is cutting through the wire. And there is a current flowing because this is a complete circuit. And I gave you a few of these. I thought it might be a useful way to remind yourself. Ryan, wire wrapped around an iron nail, which is just staying still. I asked you, is there a potential difference across the wire and is a current flowing? And you told me, no, there's no potential difference and there's no current flowing because nothing is moving there. No, we haven't got electrons or any charges that are cutting through a magnetic field. We haven't got magnetic field at all, have we? Because there's no current flowing. Wire wrapped around a magnet which is staying still. Is there a potential difference across the wire? Is current flowing? And again, we said no, because you need to have the wire and the magnetic fields like moving in relation to each other. There needs to be some cutting, and this is just stuff staying still. So no, there's nothing happening there either. And then eventually I said, okay, what if I get a magnet and move it in and out of a piece of wire? And we said, yeah, there would be a potential difference in that case. Would there be a current flowing? You get a coil of wire like that, you move a magnet in and out of it. You have got a potential difference because you've got a magnetic field cutting through a wire. But there isn't any current flowing because that's not a complete circuit. Okay, so I've got a whole new, I'm very proud of them actually. I think this is going to lead us very nicely into how transformers work. I've got a whole new set of those questions for you now. Here is a piece of wire. It's just a coil of wire, but it's attached at both ends. So it's a, what would you call it? A complete circuit. It's a complete circuit. Can you tell me what would happen in this setup? I've draw any magnetic fields, the direction of any current that should be flowing on the diagram. You can do that if you like. I'm also happy with you just to sort of shout at me. What would happen with that setup? Have we got any magnetic fields there? Have we got any current flowing? So the answer is no. That's just a bit of wire. There's no current flowing there. There's no potential difference. It's like a pen just sitting on a table. There's no difference. So there's no reason for those electrons to get pushed. There's no current flowing through that wire. It's just a bit of wire with electrons in it. No electrons moving, so no magnetic fields. Moving charges generate magnetic fields. What about this setup? It's the same thing, but now I've put an iron core inside the coil of wire. Any magnetic fields there? Any current flowing? Okay, hopefully you're saying, no, Laura, that's exactly the same as the one that you just showed us, except now there's a bit of iron in the middle, assuming that the iron isn't magnetic, because it wouldn't be, would it? Because there's no magnetic field near it, though, so it's probably not. Again, there's no magnets here. There's no moving charges. There's no magnetic fields. What about this setup? What would happen here? If you're feeling confident, you can draw some magnetic fields. You could draw the direction. You hopefully can draw the direction of the current if you've been here for a while. What's happening here? Okay, we've got a current flowing, right? Because we've attached a wire to a cell or a battery, if you haven't seen the electricity lessons. And current flows from positive to negative. So yes, I don't think I've actually bothered to put the magnetic field on this diagram, but we've definitely got a current flowing. So if we've got charged particles moving, we have also got a magnetic field. Yes. So this is an electromagnet, isn't it? It's just quite a weak electromagnet because there's no iron core in the middle. But yeah, moving charged particles generate magnetic fields. Oh, there you go. Look, I did put it in. Have I got it right? Let's double check, shall we? This is PowerPoints from a couple of years ago, and I found some mistakes and fixed them. Current flows from positive to negative. So it's going like that. It's coming out of the board on the right and in on the left. Out on the right and in on the left. Out on the right and in on the left. It's doing that, right? Yeah, it's definitely doing that. I think I've got it right. Yes. Magnetic field lines move from... Oh, I've done it again, haven't I? Yeah, I've done it again. I can see why I've got confused. Magnetic field lines go from north to south. From the north to the south. So, yeah, I want that to be the other way around. Because those arrows are moving in that direction, so I've got confused. But from the north to the south, so that's the north end of the magnet. And I should have put it down there. If you're confused, then that makes sense. Oh no, look, I've said that's the north. Oh, but yeah, it shouldn't be. It should be that would be the north, because it's moving from positive to negative, isn't it? Yeah, it's definitely doing that. Oh well. Sorry. What about this? What about this? Sort of the same setup again. I think the wire's actually moving in the other direction, and we've got an iron core in the middle. I don't think we'll worry about the magnetic fields because I'd like to gently speed up a bit. But hopefully you're saying, well, yeah, this is sort of the same as last time. We've got a current flowing, and so the moving charged particles have generated a magnetic field. But because you've got an iron core in there, it's a stronger magnet than it was before. It's a stronger electromagnet. Yeah, we've magnetised that iron core as well. What about this? What about a piece of wire wrapped around an iron core with an alternating current power supply attached? This is the symbol for alternating current power supply. So those electrons, those charges in that wire are constantly moving to and fro and to and fro and to and fro. What is happening there? Have we got a magnetic field? We have got a magnetic field. This is an electromagnet where the current is constantly changing direction. So the wire's magnetic field is constantly changing direction. So the iron's magnetic field is constantly changing direction. Look, I did a PowerPoint special effect for you. Pachoo, 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 pachoo. So sometimes the North Pole is at the top and sometimes the South Pole is at the top. Okay, what would happen with this setup, please? We've still got an iron core. It's like a sort of iron picture frame, someone was saying on Facebook yesterday. Imagine an iron picture frame with a complete circuit of wire, but there's no batteries or power supplies in sight, wrapped around one side, and a separate complete piece of wire wrapped around the other side. What's going on there? Any magnetic fields? Any current flowing? Someone said something yesterday on Facebook about things cancelling each other out. That's a very good thought, but no, we don't have things cancelling each other out here, fortunately for us. Have you said nothing? It's just two bits of wire with an iron core in the middle, isn't it? We haven't got any particles moving. There's no potential difference across these wires. So there's no reason for the charged particles to move. What about in this setup here? We've got an iron core again, and we've got a direct current now going through just one of the wires. So the other wire is just off on its own again, sitting there, a complete circuit with nothing attached. But the wire on the left-hand side is attached to, a direct current power supply. So maybe it's a battery. What's happening there? Well, we've got charged particles that are moving through a coil of wire with an iron core in the middle. So that is an electromagnet there on that side, that's set up. So charged particles moving, generating a magnetic field, iron core in the middle, making that magnetic field stronger. But it's a static magnetic field, it is a still magnetic field. So there's nothing happening on this side, is there? This is just the same as if you have, there is a magnetic field around this wire, but it's the same as if you just have a magnet still in the middle of a coil of wire. Like there's no cutting going on, there's nothing happening on that side. All right, what about this setup then? Exactly the same thing, but now we've got an alternating power supply on one side instead of the direct current power supply. What's going on there? Can you see it? I've said it before in these lessons, I will say it again. Humans are just amazing. We get a lot of stuff wrong, don't we? We're very down on ourselves at the moment because of all the plastic in the oceans and the habitat loss and the rainforest and stuff, but when we do stuff well, we're ever so good. What's happening here? Well, this is an electromagnet again, but it's an electromagnet which is generating a changing magnetic field this time. Is that okay? It's this situation. This current is constantly changing direction. So the magnetic field is constantly changing direction as well. It's flipping. Chums, what does that mean for over here? We've got a wire now, a complete circuit no less. It's just a wire, there's no battery attached. But we've got an iron core running through it, which is magnetised. And it's a magnet where the magnetic field is constantly changing direction. It's a moving magnetic field. And a wire is in the moving magnetic field. Guys, what does this mean? It means we've got a voltage across the wire. We have a potential difference. Yeah, that would even happen if it was a scrap of wire. But it's a complete circuit. So we've got current flowing. I mean, what? We've got current flowing. Sorry, I'm using a very small bit of Lego to prop you up on because I couldn't find any. We've got current flowing through a wire. There's no battery attached. It's just a piece of wire, but we've got a magnetic field which is constantly changing. So we've got current flowing through the wire. Now, why would we want to do this? Why on earth would you want to do that? If you came to our energy lessons that we did ages ago, you will know that nearly always when humans start working with energy, a little bit of energy gets wasted, right? So you will quite possibly be looking at this setup and saying, Lara, there's absolutely no way that you can have current flowing through a wire on this side and have it like generate a magnetic field which magnetizes an iron core and then makes a current flow in another wire on this side. It's not going to be the same amount of current because just energy wastage. Nothing is 100% efficient. That looks like a completely useless thing to do. And in some ways, you would be right about that, yes. We will say, in your IGCSE physics exam, they will assume, I think, that transformers are 100% efficient. So we'll just assume that the same amount of power that you put in on this side, like the energy per second on this side, is the same as the energy per second on this side, that the power is the same. In real life, it won't be because there's always a little bit of wastage, right, because of heat and whatever. But we'll say that it is. Still, why would you want to do that? Why would you want current to be flowing here? Why not just use that current? You've got some current there. Why would you want the current to be flowing there? Well, the reason we would want to do it is because, well, I'm going to answer that question more next week. I'm going to answer the why next week. We're mainly looking at the how this week. But this thing is called a transformer, and it is a phenomenally useful thing. And if you've got a laptop or a phone charger on you, you've got a transformer with you right now. We say that this is the primary coil. Don't forget, these are turns of wire, and this whole thing is a coil. The primary coil is the one attached to the power supply. And this is the secondary coil, the one that's just hanging out, chilled on its own without a power supply. I'm always going to show them on the left. It could be the primary coil on the right. Beg your pardon, don't let them trick you in an exam. If the same amount of turns are on both, then it is a pretty useless thing because you just get the voltage in is the same as the voltage out. current in more or less the same as a current out. Why would that be useful? Well, if you put fewer turns on the secondary coil, you get a lower voltage. So a transformer allows you to change the amount of voltage. And this is phenomenally useful. Have a look at your phone charger or your laptop charger and I will tell you for why. Before I start scrabbling around. Oh, this desk was so tidy until even really quite recently. Here, have a look at this one. This one's not quite as good as my other one, but you'll probably see quite a few numbers on your charger. And you'll see something called an output and an input. So here I've got the total input of this charger is, if you find a voltage, let's look at the voltage, between 100 and 240 volts input. So that's the voltage, the potential difference, if you like, going in. And what's coming out? The total output, it's sort of listed it in a slightly confusing way, but the total output it's saying is 5 volts or 9 volts or 12 volts or 15 volts, a lot lower than 240 volts. I'll get my, let's have a look at this one as well. There we go, got plenty of energy in there already. Oh yeah, this one's a bit better. 4-hour needs. It says input 100 to 240 volts, output 14.5 volts. So in another couple of lessons time, we're going to look at actually how you generate electricity, how electricity gets made. I've taught these lessons before. We've got another Transformers lesson next week. And when I taught them the first time 2 years ago, this was a really sort of quick maths free lesson, and then next week's was really heavy, so I've split it up a little bit. Next week we're going to do some maths and I'm going to tell you a really interesting, although slightly sad story. This week we're looking at what a transformer is. It's basically this iron frame with wires around it, and we will do one of the maths equations now so that we don't have to do it next week. So this will all make a bit more sense next week. But basically, when they generate electricity in the power stations, it's really good for them to be able to transport electricity to your house using a really high voltage. So the electricity that sort of comes out of your plug socket is like 230 volts. But your laptop or your phone would not do well. It wouldn't like it if you put 240 volts worth of electricity through it. So you have what's called a step-down transformer. Here we go. So transformers, you can get step-up transformers. That's what happens over at the power station to produce this really high voltage, which makes the electricity travel. We'll talk about why next week when I tell you a cool story. No spoilers. But you also get step-down transformers, which make it a sort of safe voltage for going into your home. So what you've got in your chargers is a step-down transformer. You've got something like that inside your charger right now. This is the power supply from your home, the input, which is a really, really high voltage. And because there's less turns, fewer turns on the secondary coil, it makes a far lower voltage. Now, you might be thinking, Lara, that doesn't make any sense. Like, we learned in our energy lessons ages ago that energy cannot be created or destroyed. You can't just get rid of energy. How can you get a really high voltage coming, like a really big push coming into your home, and this thing just pushed the electrons a bit less? Like how could that possibly be? It doesn't make any sense. Well, this is where we get to this equation to do with current as well. So if you're going to reduce the voltage, you're going to increase the current. Here we go. We'll talk about next week how the main thing you want is for the voltage to be high. But yeah, if you increase the voltage, you reduce the current. We will talk next week about why that's good. But that's where the energy is going. So it's not just getting lost, it's just about the relationship between the current and the voltage for the same amount of power. So if power stays the same and voltage goes up, current goes down, or vice versa. Whew. Right, you lot, let's do a little bit of maths before we go, okay? Let's crack one of these equations out. The power going in is always the same as the power coming out. I know it's not really because energy gets wasted, but we'll just say the power going in is the same as the power going out. So the power supply here putting through the primary coil, we say that, we say that it's the same as the power that eventually comes out. Which means, because of this equation, current times voltage equals power, the current in the primary coil times the voltage across it is the same as the current through the secondary coil times the voltage across it. Is that all right? Because instead of saying power, we just say current times voltage, because it's the same thing. And the power in is the same as the power out. So the current times the voltage on this side is the same as the current times the voltage on this side. So you might, in your exams, end up with questions like this. This is also terrifying, isn't it? I have no idea. I can't remember why physicists call current I. I think it's just to confuse you. IP VP equals IS VS. It's just a much shorter way of saying current in the primary coil times the voltage in the primary coil equals the current in the secondary coil times the voltage in the secondary coil. So don't worry if you are scared by that. It's just quite a nice thing to just write down in a GCSE so you don't have to write all that out. Okay, let's have a go at these questions, shall we? So these two, even if you haven't got a calculator, I think you should be able to have a little go at these. And even if you don't know how to rearrange equations, actually, because you're all in totally different places with your maths. Some of you have done loads of maths before and are really comfortable with it. Some of you have had hardly any maths practice. So I've tried to write you two questions so that even if you don't know how to rearrange equations and you haven't got a calculator on you, I think you should be able to have a little go at those. Maybe not get them right, but like hopefully they're not too terrifying. You can start thinking about what the answer might be. And if you've got a calculator or you're more confident with your maths, you can have a go at these ones. So the first transformer here, we've got a primary coil of 6 amps. That's the current of 6 and 4 volts, voltage of 4. And on the other side, we've got 12 volts, but the current is missing. So for question 1, can you please tell me what is the current going through there? Oops. So this first one, I want you to tell me what's the current going through, to basically fill in the gaps. What's the current going through the secondary coil? And for this one, I've already given you the power actually. So can you fill in the gaps here and tell me what the current is here and what the voltage is over here? Is that all right? Hopefully you can remember that power is measured in watts. So it's an awful lot of information, isn't it? Power is measured in watts. So 50 watts is going in on this side. What's the current on this side and what's the voltage on the primary coil? Is that okay? Have a little go at filling those gaps in. And if you're confident, a transformer converts 15,000 volts to 230 volts. The power output runs a 1,200 watt, that's the power dishwasher. What is the current in the primary coil? And your next question, a transformer converts 800 volts into 250 volts, 40 volts, beg your pardon. What is the current through the primary coil if the power output is 2 kilowatts? I am going to do it with you, behind you, and then we'll go through the answers. So I would always draw a diagram because it just makes me feel better. Because that's how my brain works. So I would encourage you to do the same. So first of all, you're just finding out what the current is on the secondary coil, yeah? So I think I said that I needed you to fill in those gaps, didn't I? I don't. I only need you to fill in that gap there. I should have put a little question mark. So you're just finding the current through the secondary coil both times. You can't find the current and the voltage through this first one, can you? You haven't got enough information. So you're filling in this gap here, what's the current through the secondary coil, and this gap here, what's the current through the secondary coil. Can I go through the first one for you? Are you about there? I'll just go through the first one. So you know that the amount of power going into this transformer is the same as the amount of power going out. Shush, it is. And you know that the amount of power is the current times the voltage. So you can work out how much power is going in on this side by doing the current, 6 amps, times the voltage, which is 4 amps. So 6 times 4 is 6, 12, 18, 24 watts. So the power on this side going in is 24 watts. And so you know that the power coming out is 24 watts. I'll show you what I wrote down. I did my little diagram like you're supposed to in your exam so you can tell if you've gone wrong anywhere. I said power in equals the power out, because just knowing that might get you a mark. You never know, even if you've got the maths wrong. So the power in is 6 amps times 4 watts, which is 4 volts, beg your pardon. And that is going to be the same as 12 volts times this mystery number. So 6 times 4 is 24. So you end up with, okay, 24 watts is the same as 12 times mystery number. So hopefully you can see 24 equals 12 times 2. So the answer to that first question is 2 amps. There we go, not Z amps, you know what I mean. Is that okay? Because 12 volts times 2 amps equals 24 watts, so they're both the same, and they are both the same. Should we do the second one as well? So the second one was a bit nicer because I told you that the power in on this side was 50 watts. And you know it's 10 volts coming out on this side, but you don't know what this current is. So I would just draw my little diagram again. Power in is the same as the power out. I know that the power in is 50 watts. So 50 watts in is going to be, well, the same as 10 volts times whatever this is. So again, what do you have to times by 10 to get 50? 5. Got to be careful with your units here, haven't you? We're looking for a current. So it's 5 amps. Okay, is that all right? So it was 2 and 5 was the answer. Sorry, it was very rude if you were trying to do questions number 3 and 4. If you've been to my website and you've got the free printouts, of course, you can be doing it while I'm pointing you at the screen, but I don't like to assume that everyone's got a printer. Our printer's a bit dodge. Anyway, I'll do the other 2 questions with you. Wow, these 2, you've got to be really careful. I would definitely be writing down what my output was and what my input was. In fact, I'm going to draw a little transformer again. You need to be careful what voltage you're using. Are you all right if I go through number 3? Okay, this was sort of deliberately written to be very confusing, because if I was you, certainly if I was in an exam, well, even now, my brain has to draw a picture on the board and label it, or I get really confused. A transformer converts 15,000 volts to 230 volts. The power output runs a 1,200 watt dishwasher. What is the current in the primary coil? What? Right, I've drawn that out. See if you agree. Here's my little transformer. So this is the primary coil here. So I know that it converts 15,000 volts to 230 volts. So I've said it's 15,000 volts on the primary coil, because that's getting converted to 230 volts. So I think that's okay. It says the power output, the thing that comes out, is 1,200 watts. So I've put that on that side. Be careful, I've underlined that. Like, it's definitely watts, it's not amps. And we need to know the current going through the primary coil. So we want IP. So I've gone, all right, I know that power in equals power out. So I know that if the power out is 1,200 watts, then the power in is the same as 1,200 watts. And it's also the voltage times the current. So 15,000 volts times whatever this IP mystery thing is going to be the same as the power out. So I've written that down there. And now what we need to do is rearrange this equation. So I sort of can't really help you with this. You just have to know the maths, or you don't know it really. So some of you will know and some of you won't know that if you're timesing on one side and you want to move a number to the other side of the equation, then you have to divide it. So I want to find my current. I want that to be on its own. So I've got to get rid of this over here. So because I'm timesing by green pen, it's given up. It doesn't fancy it. That's fine. I've got a red pen. Oh, that's nice, isn't it? So I need to get rid of that. So if it's timesed on that side, I can move it over here and divide it. So I can say 1,200 watts divided by 15,000 volts is the same as the current. Is that okay? It's like saying 2 times 3 equals 6. You can even, if you're not sure of your maths, I would just be sketching this in my exam. Just put in really simple numbers and see if it works. 2 times 3 equals 6. Yes, it does. Does 6 divided by 3 equal 2? 6 divided by 3. It does equal 2, yeah. So I know that I've rearranged this correctly. Okay, so now I'm going to just put into my calculator 1,200 divided by 15,000, and I get the number 0.08. Now be careful, what is that? That's a current, that's amps. And that sounds about right. I'm happy with that. If it was in the thousands, I'd probably go back and check my work. Phew! Okay, so the answer to number 3 is 0.08 amps. Let's have a go at this last one. Come on, green pen. I'm supposed to be keeping my office tidy. You can't live down there. Transformer converts 800 volts into... Okay, getting my little transformer picture on the board. Are you all okay with what a kilowatt is and the fact that you're going to have to convert that into watts before you do anything with it? Well, it's actually exactly the same thing again, isn't it? I've written here, right, easy, there we go. 800 volts is getting converted into 240 volts, so 800 is on the primary coil. And I need to know the current going through that primary coil, but I've got the current out. Are you okay with a kilowatt is 1,000 watts? So 2 kilowatts is like 2 kilograms. 1 kilogram is 1,000 grams. 2 kilowatts means 2 lots of 1,000 watts. So I have to change that into just standard watts. So it's 2,000 watts. 800 volts times this mystery current equals 2,000 watts. So again, I can get rid of this. If it's timesed on that side, I can divide it over on this side. And what's 2,000 divided by 800? I have a vague feeling that I should be able to do this. She says, stabbing into her calculator. Ah, yes, as I said, yeah, it's 2.5. Woohoo! There we go, 2.5 amps. And again, that sounds about right. Phew! There you go, chums. So the answer to that one was 0.08 amps, and the answer to that one is 2.5 amps. Right. Well, I'm sorry to stick you with quite a lot of brain exercise right at the end there, but I am happy that it means that next week, when we do our last Transformers lesson, which is the last lesson of our magnetism module, that we'll be able to just sort of tell a story and focus on one bit of maths. Because when I watched the lessons back that I'd done a couple of years ago, I thought, wow, you went really fast there, and we ended up with loads of equations at the end. So practice that as much as you need to this week, and then next week I will tell you one of my favourite stories, actually, although it is quite grim and sad, about a famous battle that went on between scientists who were debating whether direct current or alternating current was the best thing to use for generating electricity. Then we've got a week off for half term, and then we've got we're going to do a few lessons on actually how electricity gets made, and then we're going to start on solids and liquids and gases and pressure and stuff like that, which I'm very excited by, because it means that we can start grabbing household objects and doing fun activities with them again. Right, I'm on my Facebook page. I'm going to see if anyone has said hello to me. Oh, I should also say, if you want to like and subscribe, or even more importantly, pay me actual cash money for my job, that would be amazing. That is how this business works. I trained to teach physics to A-level, and now I just stream my lessons free into the internet, and I do all ages lessons, and they come with printouts. I'm so grateful, honestly, I am so grateful, because it is a ridiculous amount of work, but I don't mind doing it because I'm getting paid for it. It's such a lovely thought that whenever I'm pouring my heart and soul into it, I'm like, yeah, but it's because you've all chipped in, so it's totally worth it. Yeah, it's amazing. So thank you so much. If you want to go to my About section and click the link to coffee, then that's where you can support me with £5 or £6 a month. Hopefully not too much for what I'm offering, but for me it makes a good wage, so thank you very much. Alfred! Magnetic field will alternate direction. Nice use of the word alternating, thank you. Oh, hello Edmund, right you? Hello Jacob. Whoa! Oh, it's today, is it? Oh, Jacob's in a really cool place. Oh, yeah, it's my 4 lesson day now. Not even 3 but 4. That is very exciting. I am very excited for you. All right, Freya and Hannah. Hello. Hello, Bastian. Happy Science Day. From Rex. Rex is getting a bit of a reputation for excellent questions. Rex, what are you saying? If you put an alternating magnetic field on an electromagnet, would the magnetic objects be attracted, then drop off, be attracted again? Oh, that's a brilliant question. Gosh, that's a really good question. Would they be attracted? I'm making it up actually. I don't know. You'd have to watch one of those cool YouTuber videos where they go, what would happen if we made a bullet out of a neutron star and then shot it off Earth? I suspect it would be too quick. I think it would be too quick. I think if something was hanging off an electromagnet, then, especially if it was heavy and the force of gravity was really trying to pull it down, then it would likely fall off. But I think, because it's really switching very quickly, I don't think there'd be enough time for it to go up and down and up and down. It's a good question though. I don't actually know what you would see, if you'd see anything. Hello, Casper. Oh, hello, Rocklin. We'll go over the questions again before next week. Oh, that's good. Question 3 is very confusing, says Casper. Sorry. Hello, Kai. Hello. Alfred says the magnetic field on the left is alternating. Oh yes, nice. Oh yes, good. I am getting some excellent answers. Well done, you lot. This is probably and when we do specific heat capacity, remind me that I said this. I think next week is probably the weirdest that the maths gets, I think. When people say physics, a lot of people get really, especially people my age who maybe had bad experiences at school, get really freaked out by physics and think of it as being really hard and confusing. I think we're sort of peak hard and confusing now. So if you understood any of that, well done. You'll be all right. Oh, Xavier asks whether DC or AC comes out of a transformer. Thank you. Yes. Oh, very good point. AC. It's AC. There are various things you can do to make a alternating current be direct current, but we don't like using a diode, which only lets current through in one direction. If you've heard of a diode, but I think we did touch on that a little bit in the electricity lessons. There's Edmund again. There's Jacob. There's Alfred, Freya and Hannah, Bastian, Rex, Casper, Rocklin, Casper again, Kai. Oh, here we go. Look, it's Alfred. That's nice. Alfred says hello. Yeah, lovely. Hello to you too. I'll just go to newest comments just to make sure that I haven't missed anybody out. And then I think I might go and have some honey and lemon because I've done a lot of talking today. Good. Yeah, that's everyone. All right, you lovely lot. Thank you so much for the liking and the subscribing and the actual, paying my wages so that I can have a job. Really appreciated. I will see some of you tomorrow for the eels lesson, the Lego eels show, or for the Lego lesson that we're doing. The all ages lesson topic is Lego at the moment, isn't it? About design. Well, I'll see you next week for the last Transformers lesson. Bye.